Good day, everybody. Today we're going to look at a trig problem, and that's trying to find numbers where the sign of that number evaluates to the same result, whether you're in radian mode or degree mode. It's kind of similar to sometimes as an easy check if you're in radian mode or not. You can take the sine of 90. If you take the sine of 90 and get 1, you know you're in degree mode. And if you don't get 1, then well, you're probably in radian mode. Easier than 90 is 0, but if you take the sine of 0, it's going to be 0 in either mode, radian or degree. And so my question is, find all numbers so that you would get the same result, whichever mode you're in. All right. So kind of subscript if I'm doing in radian mode, but using most software, the radian mode is the default. So sine of radian mode will be sine of x. So if I plug in, say, pi over 2, I want to get 1. If I want in degree mode, I'll subscript with it d. And, well, if you have a radian mode software or whatever, evaluator, you can evaluate sine of your degree number times pi over 180. So if I want to evaluate sine of 90 in degree mode, if you plug 90 in here, it'll end up evaluating the sine of pi over 2, which will be 1, where this is, of course, in radian mode. So our question is to solve sine in radian mode equals sine in degree mode. And, well, we see sine in degree mode is pi x over 180. But sine is 2 pi periodic, so sine of x is going to be the same as sine of x plus 2n pi, where n is any integer. So if I put that in here, then sine of x plus 2n pi equal to sine of x times pi over 180. I want that to equal, so I need the arguments equal, x plus 2n pi. And just doing a little bit of simplifying here, I'll subtract this term to the other side, move this over, but n was any integer, so I just replaced it with the negative of n. Sometimes I change it to a different letter like m, but here I left it. But any multiple integer multiple of 2 pi is all that matters for all integers. And then when I subtract this over, if I get my common denominator and then solve for x, I get this value. So all these numbers work. It's not the full result though. And I first saw this, someone else, I gave it to another person as a challenge, and they solved it and they got those values, but some others as well. So looking at the way they did it, let's go back. We're solving sine in radian mode equals sine in degree mode. So again, this, but here to be subtract, and then we use a known trig identity. So if I replace, a and b are my x and pi over 180x, then it's 2 cosine of 1/2 the sum, sine of 1/2 the difference. And so so now it's a product. So for cosine to be 0, I need this argument of cosine to be some odd multiple of pi over 2. And so I can just double both sides, get that pi, get my common denominator, and solve for x, and then I get this value. So I didn't have these values before. So these are new values, so all odd multiples of this quantity. The other way to get 0 is to have the argument of sines, any multiple, an integer multiple of pi. So sine of an integer multiple of pi will be 0. So I need the argument of sine to be an integer multiple of pi. So again, I can double both sides, and if I solve for x, these are the values I had before. So to sum up, there's the set of all solutions, all x's. So if x is any of those values. If I go back, so I can get those values. So here's where I left off, and I just plugged in for sine. Sine equals, since sine is 2 pi periodic, sine of x plus 2n pi. But another way to get sine is if you take the negative of sine and then shift it an odd multiple of pi and any integer. So we see that here. So here's sine. Again, if I shift it any multiple of 2 pi, it'll be the same graph if you go infinitely. But negative sine is then dashed in blue. And now if I shift that pi units, and then from there any even multiple, so altogether shift it any odd multiple of pi, I will have the same graph as sine x. So using this identity that sine x is the negative of sine of x plus an odd multiple of pi, I can put that back into here, replace this left-hand side, and so we want to solve this equal to sine of pi x over 180. Now sine is an odd function, so a negative can come into the argument, and so this will be the argument if I bring the negative into the argument. So I need this to equal then the argument of the right-hand side. It's just that. So if these are equal, and again, so I'll move this to the right-hand side, and this time actually I'll leave this on the left, add the x to the other side, and if I solve for x, I get those same values as before. So these are the other values. So there's these values, 360 times pi over pi minus 180, and 180 pi plus 180, odd multiples of that, any multiples of this. So again, that was the same as what I had here. So it seems somewhat straightforward for cosine. Similar argument, cosine in radian mode, cosine in degree mode. If your software evaluates in radian mode, you'd need to do this. So for example, if I want cosine in degree mode, if I want cosine of 60, it'll be 1/2. Well, if I plug 60 into here, I'll get cosine of pi over 3, and that'll be 1/2. So again, we want to solve cosine in radian mode equals cosine in degree mode, but that'll be cosine x equals cosine of pi over 180x. And this time I'll do the subtraction first and use this difference of cosines identity, 2 times the sine of the sum, and sine of the difference, it's actually b minus a, or a minus b first. But so the difference here will be 2 times the sine of 1/2 the sum, and then sine of b minus a, so like that, equals 0. And again, how can that be 0? It's if the argument of sine is n pi. So we quickly solve to get this. Or if this argument is a multiple of pi, I have m pi, and so we get this. So these look pretty similar. That denominator is negative, and since m is any integer, I rewrote it this way to have a positive quantity, but over all integers. As I did with the sine, well, where I put them equal to each other, and then I replace cosine. Well, cosine again is 2 pi periodic, so I need x plus 2n pi to be equal x pi over 180. And again, we get part of the solution from before. So this is the part we had. For the other part, again, another way to get the graph of cosine is to take the negative of cosine and then shift it an odd multiple of pi. We probably don't need the graph to see that, but in black's cosine, the negative is blue, and then shift it pi. So that's another way to get the graph. So I can say the negative of cosine x plus an odd multiple of pi equal to cosine of this. So this was cosine of x, but now it's that. So just to see how tricky I had to be, if I want the negative brought in, cosine's even, so I can't bring it in. But there's another identity cosine. I mean, they're cofunctions. So cosine of an angle is the same as sine of pi over 2 minus the angle. And so I did it here too. So cosine, just keep the negative factored out. Cosine of this angle is the same as sine of pi over 2 minus that angle. And now that I have it in sines, I can bring this minus in and then equate the arguments, and I get the other values. So those are the full values for cosine. Here's some of the, here's a graph of what we're looking at. Now you remember in red is sine in radian mode, and compared to degree mode, it looks a lot more frequent, right? So in degree mode, you reach your peak at 90, and then you'll have the x-intercept there at 180, and so on. You'll go on forever. But these peaks always go to 1, so I mean, you keep intersecting. So this is sine, and we found them all. Of the first set, my first angle is at around 6.4. Of the second set, my first angle is around 3. Angle number, I should say. I don't know if I should call it a number. Let me shrink this down to say 12. All right, so a little over 3, and then a little over 6, and then it'll be odd multiples of the 3. So the next one will be at 9, and then 12. Right, so I've got the 3 one. I mean, it's more than 3, but 3, and then triple that, and then 5 times this, and so on. And then here's the 6, and then double. And so those are the intersections for the sine. So even multiples of this 6.4, odd multiples of the 3.08, no less than pi. So here's the graph of cosine in degree mode, and we'll start at 1 and then hit at 90. Here's the cosine in the radian mode is in red. I'll go to 200 again. So we found those intersections. These are actually the same as with the sine, so it's a repeat. And any multiple of this value as well. So the 6.1, 6.39. So again, they're close, but they start to separate a little, and then they'll get close again, right? So the two intersections are close for a while, but gradually they get more separated, then they get close again. And that's what happens. So their difference is kind of close at first, around 0.2. All right, so lastly, with the tangent, again in radian mode and in degree mode, we want where they're equal. Tangent is pi periodic. So tangent of x plus n pi is tangent of pi x over 180. So if I put those equal to each other, the arguments, do a little extra work here, and then subtract this, move that over, and any integer, this time I replace with a different integer, and solve for x. And for m even, these are the same values we got with sine and cosine. So for m odd, it's actually new values. And another way to do it, maybe we'll look here. If I want to solve where tangent in radian mode equals tangent in degree mode, if you cross multiply and then subtract, you get this, but that's just simply sine of a minus b, where a is the first and b is the second argument there. So I essentially, if I have this equal to 0, it's the same as sine of x minus pi over 180 equals 0. And so again, I get that solution I had on paper. 180 pi over 180 minus pi times any integer. And just to look at the printed version for cosine, we'll go in reverse order here. It was the union of these two sets of numbers. Again, for the even values, it matched here, but this also includes odd values of 180. And even values would give me a multiple of 360. And for sine, again, redoing the work, but here's a look at what the set of solution values looks like. And so again, we've got any integer multiple of 360, which was the even multiples of our tangent. So those are the solutions. Note, tangent is pi periodic, but that's it. There's no other way to get the tangent other than to shift it a some multiple of pi. Right? If I do the negative of tangent, like in the dashed here, and then shift, I can't recover tangent. So the only way to get the tangent was just that one way. So that's why there's only the one set of solutions, which we saw two different ways. Right. So here, there's only the one way to get the solutions, because there's only one way to get tangent. You can translate it, but you can't negate it and also translate it. All right, so that's the result. Fun little challenge problem. Regardless, hope you had a good time watching the video. Thanks, and have a good rest of your day.